let me remind you all that, the class Friday, I'm probably gonna post I won't be here on Friday, so I'll post the videos, probably tonight. Uh, I should be back Monday. Everything should be hunky dory. I will email you if that's not the case, in which case I'll record videos from Monday's lecture, but I should be back by Monday. Okay, so we're doing some fun stuff. We're talking about how to compute Galois groups, at least for selected kind of things. So in general, if you have R1 up through Rn being roots of some polynomial here, because actually doesn't have to be irreducible, we define delta to be the product of Ri minus Rj, and of course we've pre-selected some order. It doesn't really matter what order the roots come in. And we define the discriminant to be the square of whatever this is. So for example, if you have R1, R2, and R3 roots this cubic, then the discriminant is, well, the delta is this, the discriminant is squared. In fact, let me follow the proposition. So proposition. And delta is in K. Delta is in K if and only if the Galois group of F, which equals the Galois group of F over K, the splitting field where F little f over K is contained in A.
Dr. Gordon,
Mm-hmm.
right there, that and, are you meaning like both of the first two statements are true if and only if the second stuff, or like these are two separate things?
No, this is always true.
Yeah, okay.
And this is true if and only if the Galois group is contained. So how can you tell this is in the base field, right? So this is the first claim that D is supposed to contain the base field. Well, you can multiply this out and start playing with the coefficients, but please don't. Notice, if you have any element of the Galois group, it permutes these roots, right? And any permutation of these roots is invariant on D, right? So for example, if I swap R1 and R2, then this is the same thing because you're squaring it, right? This is R2 minus R3, which is this, and this is R1 minus R3, which is this, right? If you do any permutation of the roots, this thing is left over. And since the splitting field of whatever that polynomial is, and we're assuming the polynomial is separable, then it's Galois. And so that means that that thing has to be the base field, right? Yes.
What did you said the D is always in K, but delta is only in K
if and only if the Galois group is contained in AN. Now, look at this one. What happens if you do an odd swap, right? So what happens if you swap R1 and R2 to delta? It changes the sign here and it leaves these two alone. It just swaps these two. Agree with me? So notice that odd permutation. What happens if you swap out R1 and R3, right? Well, that changes the sign of that, and it changes the sign of that, and it changes the sign of that. Right, so let's change the sign. Everybody agree with that? What happens if you do an even permutation? What happens if R1 goes to R2 and R2, what happens to delta if R1 goes to R2, which goes to R3, goes back to R1. So that's a 3 cycle, so that's an even permutation. And this turns into R2 minus R3. This turns into R2 minus R1, and this turns into R3 minus R1. And notice what we've done is this pairs off, this sign has changed, and this sign has changed. So there's a net no sign change, right? That's the guts of this theorem, right? Because what happens is, if you're in A3, then this is invariant and therefore in the base field, right? On the other hand, if the Galois group, has an odd permutation, then you can change the sign of this, meaning this is not invariant anymore, and so it can't be in the base field. So that's essentially the guts of this. Everybody kind of get the gist of it. Yes.
Is that AN like related to, like, is that a
Multimeasure
specific,
group on letters.
but is it a specific N? Like, is it like the degree of F or?
Mhm.
Okay.
Okay. Let me give you an example. Well, it's really kind of more than an example, I guess. And I probably should do it here. I'm doing a few things. All right. Not one of these. Maybe. So, if you have a cubic polynomial of this form, suppose you have x cubed plus ax squared plus bx plus c, then the discriminant of this is given by a squared b squared minus 4b cubed minus 4a cubed c minus 27c squared plus 18a. You can do this, right, if you're extremely a patient person, by just letting this be x minus R1, x minus R2, x minus R3, and doing the computation. It's obnoxious, but it can be done, right? So, for example, if I give you the concrete polynomial x cubed plus x squared plus 1, so it won't over cube, then the discriminant is equal to, here, let me make my life easy, a equals 1, b equals -2, c equals -1. That is going to be, I guess, 4. That's going to be plus 32. That is going to be plus 4 minus 27. And let's see, ABC is 2, so that's plus 36. I hope, which is 1340. That's right. So for this particular polynomial, this means that this is a square. Q. So delta is in Q. So in particular, the Galois group of this polynomial is A3. Isomorphic. Because this is, I didn't prove this for you, but it can be shown that this is an irreducible polynomial. Well, actually, can somebody tell me why this is irreducible? There's a good way to do this. It's not Eisenstein. I mean, you might be able to make a change of variable to make it Eisenstein. There's another way. This is cubic, and cubics are easier in the following sense. If this reduces, it has to have a rational root. Everybody agree with that? How many of you remember the rational root test? Well, this is part. That. This is true over any integral domain. So if you have a polynomial of this form, then, well, actually, you can't do it more generally. We'll do this over U of D. Then any rational root, that is in quotient field, R is a form. So, there was somebody cleaning board class, it's still wet, so it just needs to dry out.
Oh, well, that's shut up.
So, any root, any rational root in the quotient field is in the form, let's say, alpha over beta, where beta divides AN and alpha divides AC. How many of you have ever seen this? Right, rational root test. So any rational, any quotient with any quotient with numerator, denominator, and R has to satisfy that the numerator divides this and the denominator divides this, right? And we've got a rather easy numerator and denominator thing to deal with here. Here we're over Z, and the only divisors of 1 and -1 are plus or minus 1. So if plus or minus 1 are not roots of this, then there are no rational roots. Thank you very kindly. So there are, so if plus or minus 1 don't work, then nothing works as far as rational, and you can test them both to see if they don't, right? I hope. Anyway, yes.
When you say in quotient field over R, is that like R over like R mod? Or what is?
No. So, K equals quotient field R. Which is the set of A over B, or A and B and R, and B is not 0. Right, like the rational numbers are to Z. So there's no rational root to this. So that means that polynomial has to be irreducible. So its Galois group has to be a transitive subgroup of S3 because it's a degree 3. So it's either S3 or A3. And the discriminant in this case tells me that it has to be a subgroup of the alternating group. That's the only alternative. This Galois group is cyclic of order 3.
Does it being a square, or what does it being a square have to do?
That was that previous proposition that,
Oh, because then this.
yeah, the
Okay.
square root of this is the delta,
Mhm.
right? Which is 7, which is rational. If this had been 46,
Mhm.
right, the square root of that is not rational, and the Galois group would have been S3.
For the reals, would the reals always, is
Oh,
delta always in?
not if it's negative, right? So for example, you might have, so what could happen in the reals, and this is like your quadratic formula thing. In the reals, what's happened is if your discriminant is positive, then it's got 2 real roots. If your discriminant is negative, it's got 2 complex conjugate roots, so dynamic real roots. So in the first case, for the reals, what happens is the Galois group is the identity, because the real roots are already there. And in the second case, the Galois group is S2 because you have 2 adjoining complex numbers together. Okay. We're now going to deal with quartics, and this one's a little bit more long-winded because there are 5 transitive subgroups of S4, and I'm going to sort of go through an algorithm where you can figure out what the Galois group is for a quartic. I'm going to focus on being over Q, but this you can generalize this fairly easily. So here, what I'm going to do is I'm going to let big K field, and I want the characteristic of K be not 2. F is an irreducible polynomial of degree 4. Irreducible of degree 4. And separable. Irreducible, separable of degree 4. We'll let G is the Galois group of F, and what that I mean by that is the Galois group of the splitting figure of that polynomial. Lemma. Let R1, R2, R3, R4 be the roots, and of course they're all distinct, of f of x in a splitting field. And I'm going to define these little gadgets here. Let alpha is R1, R2, R3, R4. Beta is 1, 3, R1, R3 plus R2, R4. Gamma must be R1, R4, R2, R3. Let's let right. So notice that I wanted to introduce this. Let's let V you might think the way I've set these roots up might be kind of familiar, and there's a reason. this is normal in S4. So this is that Klein-Fuller subgroup that is normal in S4. The field K alpha, beta, gamma corresponds to the normal subgroup that's normal in G. So alpha, beta, gamma is Galois over K. With Galois group G mod G intersect V. So let me say a couple of words about this. Notice this subgroup is set up to leave alpha, beta, and gamma alone, right? Because notice that any of these automorphisms, if you swap 1, 2, and 3, 4, this leaves alpha alone. 1, 2, 3, 4 leaves this one alone. And swapping 1, 2, 3, 4 leaves this one alone as well. And same for the other ones. Everybody agree with me? And so what happens is this thing is fixed by V. And so hence the statement. This is Galois over K because it corresponds to this normal subgroup. This is normal in S4. And so its intersection down within the Galois, whatever G is, it has to be the transitive subgroup of S4 is normal in here. And that's the statement. And we are going to use this. This one is going to be key in figuring out what the Galois group is. So, now this is also, how many of you, by the way, how many of you have ever looked up the Cordic formula? You ever, it's awful, isn't it? Well, I mean, the first thing you got to do is you got to tackle this cubic, and then you go on to do this. And this is because the possibilities of the Galois group are nested in a certain sense. Here is the analog here. Let K be a field. Notation continuing. Let F of X equal mnemonic, I guess. X4 AX cubed plus BX squared plus CX plus D. So you've got this polynomial here. So we're finally writing out its coefficients. The resolved cubic is R X. Actually, this will actually work for any polynomial, whether it's here it is or not. Is X cubed. And here's the only theorem part, so I'll tell you what this is. Minus BX squared plus AC minus 4D minus A squared D plus 4BD minus C squared. Right. And this is actually x minus alpha, x minus beta, x minus gamma. For our old friends alpha, beta, gamma here. So the only part to this really proposition is just verifying for yourself that when you multiply this mess out and knowing that these are the roots of this polynomial here, setting things up and showing that this turns out to be what you want. This is called resolve cubic. Now, let me give you a theorem that I'm actually only going to apply. So I'll state this a little bit as generally as I can. Theorem. Let's let K be a field. And let's see, F, an irreducible quartic with distinct roots. Irreducible and separable. So it's an irreducible polynomial. It's got distinct root. We're going to call this Galois group G. G, which is a subgroup of S4. In fact, it's going to be a transitive subgroup of S4. Let alpha, beta, gamma be the roots of the resolvent cubic. Resolvent cubic. And M being the degree of K alpha, beta, gamma as a field extension over K. Then, number one, the degree of this extension is 6, if and only if G is isomorphic to S4. Two, M is 3, if and only if 6. G is isomorphic to the alternating group. M is 1, meaning all those roots of the resolvent cubic are already in K. If and only if the Galois group is isomorphic to V. So let's decline. Oh, I mean, this is the only other possibility too, if and only if G is isomorphic to C4 or D4. And how do you tell which is which? Well, G is isomorphic to D4. If and only if F is irreducible over K alpha beta. So if you get the degree of the extension is 2, then you look back at your original F and ask if it's irreducible over that quadratic extension or not, and that tells you whether it's cyclic or not. So let me let's look at some examples here. let's look at f of x first. B. X4 plus 4x squared plus 2. I've created these polynomials just to make our lives a little bit easier. Lots of zeros. A equals 0, B equals 4, C equals 0, D equals 2. And so, resolve with cubic. There's one thing I need. Let me actually put the result cubic over here, and so we'll. So let me write down the result. I'll put it right here, so we can use it again. R equals x cubed minus bx squared plus AC minus 4D x minus a squared D plus 4BD minus C squared. There's result in cubic. So here, R is going to be x cubed. B is 4. Right. AC minus 4 AC, which is 0, minus 4D is minus 8x. And A squared D is 0, 4 BD is I guess 32, and C squared is 0. Oh, yes. Y'all see the root of this? Assuming I did this right, we better check me here. A is 0, A, B, minus 4x squared. Let's see. It's 35, 0. That looks right. And minus A squared. It's gone. Plus 4B. Okay. Okay, so do y'all see a root of this? Okay.
The square root of 8.
This is x minus 4, and this is x squared plus 8. Is that right? That look correct, y'all? And so we need k. So the roots are 4 and plus or minus 2 radical. Whoops.
Should it be minus 8?
Oh, maybe you're right. Yeah, you're definitely right. So fix that. So the roots are those, right? So in this case, k alpha beta gamma is q adjoined with the square root of 2. Everybody agree with that? Because adjoining 4 doesn't do any good, plus or minus, right? It doesn't matter. And so m in this case is what?
2.
It's 2. So this is this bifurcated thing here. So already I know it's either cyclic or 4 or it's dihedral, right? So let's look at f of x. Does this reduce? I think it probably does, right? Because notice. So the roots of this are x4, I'm sorry, x squared is equal to plus or minus, I'm sorry, is equal to minus 4 plus or minus the square root of 16 minus 8. So this is minus 2 plus or minus radical 2. Everybody agree with that? So this polynomial should reduce. This should be x squared minus 2 plus radical 2 and x squared minus 2 minus radical. Everybody agree with that? So it looks like a Galois group of F is isomorphous. Cyclic Galois group looks to me like. Everybody okay with it? Okay, let's look at another example. How about I actually look at a couple more. X4 minus 10x squared plus 4. How about better get that right? Yes. So here we have A equals 0, B equals -10, C equals 0, D equals 4. My resolvent cubic is x cubed plus 10x squared. Let's see. Any A and C is dead, so that's going to be minus 4D, so that's going to be minus 16x. And that's going to be 4BD. That's going to be minus 160. Okay. Oh, I see how to factor this one, I think. This is x squared times x plus 10. You know, when people start doing this, when you're grading calculus, this is when you start to really get nervous that, you know, the whole thing's going to crash into a mountain. But here, that looks right. So this is x squared minus 16, x plus 10. Right? Oh, look at that. That's got like 3 real roots. So minus 10, 4. Right? So here, the degree of the extension is 1. So Galois group of F is isomorphic to the Klein formula, Z2, Z2. Finally, let's look at f of x equal x4 d plus 2 minus 2. In this case, A equals B equals C equals 0 and minus 2. So the resultant cubic is x cubed plus 8x. And that's it. Which equals x times x squared plus 8. Now, what you have is k alpha beta gamma is actually q adjoined with the square root of -2. So again, m equals 2. Right. So once again, we're in the case where we've got to make the choice of what happens here. If you look at the polynomial, x to the 4 minus 2 does this reduce or not? Yes.
For like the degree of the extension, like since square root -2, like why is it not like why don't you have to join I or like why can you have it?
Because you joined radical 2i,
Okay,
right? I mean, that's essentially what we've done.
so would that mean that regular radical or like the real radical too is in it
No,
or no?
no, only I times I is in there. That's right. So this is and this is, I can factor this all the way down to this playing field, x minus, let's see, 2 to the 1/4, x plus 2 to the 1/4, and this is x plus I 2 to the 1/4, x minus I 2 to the 1/4. And I'll let you check that no matter how you put these together, you never get a reduction in Q adjoined with I. You only get your I's attached, well, we'll see. You can get, right. The only way that you can get, which is Q, I 2 to 1/2. So you can check this out. I mean, certainly you can get a factor here that looks like it's in there, but what happens here is you get cross terms that are not in there. So no matter how, this actually doesn't reduce over this. So what you get here is 4. Okay. Any questions on that? So here is a more sweeping theorem, and I'm gonna write this out, and then I'll tell you the tragic story that goes along with it. Here's a theorem. Suppose f of x is monic of degree n and cx and p of positive prime c. Suppose f of x is monic in cx. It doesn't really have to be, and p a positive prime, as long as the leading coefficient is relatively prime to this p. We also suppose the reduction of f of x modulo p has distinct roots. Degree n. We suppose the reduction of f of x mod p has distinct roots, which it will for most primes. And some extension of z mod p, when we reduce mod p, then if f of x factors g1x up to gkx with gix irreducible in zpx. So just take that polynomial's reduction mod p and factor it into irreducibles. The degree of each gi if degree of each gi is mi, then there exists sigma in the Galois group of f, that is the splitting field of that polynomial. And of course, I mean the Galois group over Q of the form C1, C2 up to CK, with the CI's disjoint cycles of length mi. So in other words, under these conditions, you can go mod P and factor your polynomial. And if you satisfy these modest conditions, when you factor the polynomial mod P, just look at the degree of these polynomials. There has to be an element of the Galois group of this over Q that has exactly K cycles, each of the length, the degree of this. Here is a tragic story. I gave a calculus problem one time. I have this parabola, so this is 0.10, and I asked my calculus class, find M such that the area in first quadrant is divided into two equal pieces. Right? So let's take this area here, find the slope that breaks it into two pieces. And something like this. If you work it out, and it's not too difficult to set up the integral, you got to make this part equal to this part, set some stuff up, and you get an equation. I think this is what the answer is. You end up having to solve a cubic, but it's a perfect cubic, and you can take the cube root. And of course, I gave most of the credit to the people that got it set up most of the way in. A couple of people got all the way. Well, I had this person who missed the exam, missed it again and again and again, and I had to give him a makeup test, and I remade it several times because he kept missing it. And so I had the nth iteration when he finally showed up, and I said, okay, how am I going to replace this problem? I was in a hurry. And I said, well, I know what I want to do. Instead of dividing the area, let's find the slope so that when you revolve this around the x-axis, it breaks it up into two pieces of equal volume. The principle is the same, right? The setting up is not much more difficult, except you have to do it with a volume. So for volume, it turns out the polynomial that you need to solve to get M in terms of A, get this. So you get a polynomial in the variable M over A, and that polynomial turns out to be 8x to the 5 minus 10 x to the 4 plus 1. And believe me, I did some reducing to get this. Let's apply this theorem, shall we? It turns out that you can reduce this polynomial, reduce mod 11, and what happens is you get 8x5 minus 10x4 plus 1. If you treat this mod 11, this is actually 8 times quantity. I pulled the 8 out. X squared plus 9x plus 6 times x cubed plus 9x squared plus x plus 3. It's easy to check, but it's obnoxious. that both of these polynomials are irreducible over the field of 11 elements. What does this mean about the Galois group? Well, notice that there is a 2 cycle times a 3 cycle. Right? So the transitive subgroups of S5 are cyclic of order 5. That element's of order 6. It's not that. Dihedral on the pentagon. That is of order 10. That's of order 6. Not in there. This is not in F20 because 6 doesn't divide 20 either. This is not in A5 because this permutation is odd. The Galois group of this polynomial is S5. So, poor little student. The moral of the story is don't take a makeup and make you in a hurry. Any questions on that? So this is very powerful because it allows you to kind of figure out, you can eliminate a lot of things. This can't, just by that cycle decomposition, this can't be 4 out of the 5 possible Galois groups that it could. Yes.
Why did we do mod 11?
Oh, because the other ones didn't work for me,
Oh.
right? There were various problems. Mod 2 is a big problem here, right? Because this drops out. And so so you might ask what happened mod 3, 5, and 7. Well, what happened is it reduced into polynomials that gave other possibilities, right? The Galois group of this is S5, so every possible permutation can come up, right? The other ones gave me permutations that didn't allow me to eliminate things. 11 was the best one. Okay, other questions? Yes.
When do we know that it would be something else? Like, if you did this reduction and then you said, okay, I know that it could be, let's say, like C5, you know, like, how would you know that? If you have a 5 cycle, it could still be in
That's right.
F5. Yeah.
You don't.
Yeah.
So there are bounds on checking things. I mean, you can certainly do something probabilistically,
Sure.
right? But there are other kind of bounds that are beyond what we've done so far, right? But you're right in the following sense. This is best for elimination, not verification, right? So, okay, others. All right. Well, I will see you folks